It's difficult to put into words how fortunate we are to have the Cassini-Hien mission, one of 4 robotic probes, to visit Saturn. However, of these missions, Cassini-Hien has had the greatest impact, both scientifically and practically. Its data has served as the foundation for more than 4,000 research papers. It has found 6 new moons and shed light on their composition. It has survived 20 years of traveling 7 billion kilometers, and has spent 13 of those years orbiting Saturn, collecting data on it. Along with providing some of the most breathtaking and awe-inspiring images of Saturn and the solar system to date, Cassini continued to gather data right up until its final moments as it plunged into Saturn's atmosphere and broke into thousands of pieces. It was an incredible mission. I'm Alex Mullen, and you're watching Asam. Join me today for this Cassini supercut as we explore it. The Pioneer 11 probe was the first to reach Saturn in 1979. Scientists confirmed that Titan, Saturn's largest moon, had an atmosphere at that time, so they knew they had to return and further study the planet. In the grand finale, we learn about the time leading up to the dive, what the spacecraft found during the dive, and the incredible discoveries that have been made from the clues provided by Cassini-Hiens. If you want to see Saturn's beauty, you must watch through the eyes of Cassini. Land on the moon in 1997, the Cassini-Hien spacecraft was born. By the time Voyager 1 and 2 were already en route to Saturn, it was too late to include a lander in those missions. Reaching Saturn is no easy feat, as the entire journey involves fighting the sun's gravity, which tries to pull Cassini back to the inner solar system. To help achieve the speed needed to reach Saturn, the spacecraft flew past Jupiter and other planets that act as gravitational assists, past Venus twice before circling back to Earth. After that, it was propelled towards Jupiter, which provided the last push necessary to reach Saturn. This particular alignment of the planets only happens every 600 years, so the timing was crucial. Cassini barely missed Earth on its second pass as well, coming within 1,100 km of the surface. What's more intriguing is that it was actually powered by 3 RTGs, or radioisotope thermoelectric generators, were the main power source on Cassini. The power came from approximately 33 kilograms of radioactive plutonium, which decayed into electricity. Even at the end of its life, the spacecraft continued to produce around 700 watts of power. The problem was that if scientists had miscalculated and the spacecraft had crashed on Earth, all inhabitants would have been exposed to radiation. Now, 33 kilograms isn't a huge amount, but since the likelihood of this occurring was low, NASA deemed it an acceptable risk. Nevertheless, in the worst-case scenario, it could have resulted in 5,000 cancer deaths. Cassini relied on RGS because solar panel technology wasn't advanced enough to power an object so far away. With RGS, Cassini would have had a very long operational life and could have continued even after it ran out of propellant fuel. Cassini had many goals to accomplish. Hiens, a lander attached to the Cassini spacecraft, was designed to see what was going on under the hazy clouds of Titan. It was built and operated by ISA, the European Space Agency. The mission's goals were to understand the structure and dynamic behavior of Saturn's rings, explore Saturn's moons more fully, measure Saturn's magnetosphere, study Saturn's atmosphere, and conduct more extensive studies of Titan. This video is an actual Spartan version of the 21-hour descent. The main mission of Hans was actually to take readings of the atmospheric pressure, composition, wind speed, and so on during this descent. The probe, which was 13 m wide and weighed 300 kilograms when it detached from the orbiter, spent 22 days in space before entering Titan's atmosphere. At this point, the only system on board that was active was a wake-up timer, which was utilized just 15 minutes before entry. What the probe saw when it woke up was truly remarkable. Due to the mission's limited objective of measuring atmospheric readings, the battery life was not anticipated to be extended beyond the landing. The scientists had anticipated landing on an ocean or lake and had constructed Hien accordingly. However, as you can see, it actually landed on what appears to be the bed of a dried-up lake. The mission of Cassini has been quite successful, and the scientific data it has collected over the past 13 years has contributed to some of the most breathtaking space images ever discovered. I simply want to showcase a few of my favorites of Saturn, and of course, Saturn's moons are stunning as well. Some truly committed souls have even taken 1 million photos taken by Cassini to give us an idea of what it would be like to be on the spacecraft. These are actual images, only enhanced and color-corrected to show movement. No computer-generated imagery here. It's absolutely mind-blowing. As Cassini's fuel ran low, scientists started to consider how, in an effort to gather as much data as possible in the limited time available, they instructed Cassini to fly by Saturn and its moons at unprecedented closeness to the gas giant and his rings. The mission began on November 30th, 2016, with Cassini repeatedly ascending above Saturn's north pole and descending to a point just outside the narrow F ring, which serves as the edge of the main rings. After 20 orbits, on April 22nd, 2017, Cassini would leap over the rings. In the Cassini grand finale, the spacecraft began its last series of daring dives between the planet and the inner edge of the rings. The probe progressively approached its target, putting itself in ever-increasing danger. As the mission neared its end, its data became increasingly pure, but as it soared into Saturn's embrace, its chances of annihilation became certain, according to NASA's website. Thanks to Cassini's particle detectors, we will have a much better idea of how much material is in the rings, which will bring us closer to understanding their origins, and the spacecraft will create detailed maps of Saturn's gravity and magnetic fields, which will reveal the planet's internal structure and, perhaps, help solve the own mystery of how fast the interior is rotating. The original mission planners might never have imagined the wealth of information that Cassini will gather. Instance, icy ring particles being drawn into Saturn's atmosphere by the planet's magnetic field, and its cameras will capture breathtaking ultra-close images of the rings and clouds. No other mission has ventured into this unique area so near to the planet, and what we learn from these endeavors will enhance our comprehension of the formation and evolution of giant planets and families of planets worldwide. As Cassini nears the end of its 20-year mission, it will ensure the biologically fascinating worlds of Enceladus and Titan, which may have hidden microbes and survived the voyage unharmed, would never be contaminated. It's a fitting conclusion to the exciting story of discovery, and it's inspiring, adventurous, and romantic. But before we get too carried away, let's examine some of these last moments during Cassini's grand finale. NASA was willing to trade Cassini's chances of longevity for an opportunity to get unprecedentedly close to Saturn. It was an easy trade to make considering Cassini's time on Earth was running out. This decision meant Cassini could approach the planet darting in between the rings closer than ever before, which meant its survival was already out of the question. But what did it see? Did this unique perspective reveal anything new? Let's take a look at some of the amazing sights Cassini saw during its grand finale. Starting with the moons of Saturn, it saw some of the shepherd moons in unprecedented detail. This is a close approach of Atlas, a 40 kilometers wide moon near the outskirts of a ring. The moon's seemingly flawless surface devoid of impact craters gives it an eerie disk shape, and dust from Saturn's rings settles on it, especially near the moon's equator, giving it that appearance. A similar process occurs with Pan, Saturn's second innermost moon, which is 30 kilometers wide and located in the Anchor Gap. Any ring particles that wander into its 350 kilometers wide path are collected by Pan, keeping the Anchor Gap stable. This is another shepherd moon, constant gap. It's not visible in as much detail as the last one, but its effect can be seen for hundreds of kilometers due to the gap it's in. The moon is only 8 kilometers across and lies in a narrow A-ring crater called the Keela Gap. Its gravity is weak, but it's just enough to where nearby dust particles as it brushes by, creating waves and ripples in the nearby rings, and even ripping material out of the rings themselves, as observable in this little trail. In this case, the ripples aren't just moving laterally. They're also moving vertically, as seen in the shadows they cast. Sitting on Dnes and watching the waves as they follow Saturn's orbit would be an incredible sight. Speaking of the rings, Cassini has taken some breathtaking pictures, including this one of the Janus 21 spiral density wave, which is truly astonishing. This is an example of a spiral galaxy that has been formed through the same process as spiral galaxies, but with a much more compact structure. Instead of what seems like multiple rings, there are actually just two spiral arms that circle the planet multiple times. Each of the two lines in the image corresponds to one of these arms. This particular image is of the B ring, which is located at an orbital resonance point where the ring orbits twice for every orbit of Janus, Saturn's moon. The photo appears to be tilted to the top left, but that is not the case. The phenomenon is brought about by the distorting effect of the planet's density waves, whose wavelengths decrease as one moves away from the resonance. The fact that the moon, which plays a role in the resonance, switches places with its neighbor, Epimetheus, once every 4 years causes the rings to react by adding a new wave crest. According to NASA, the distance between any two crests is equal to the length of a wave traveling downstream from the planet. The wave here encodes the orbital history of Janus and Epimetheus, which spans many decades. The section of the wave at the top left of the image corresponds to their positions during the voyage of flybys in 1980 and 1981, when it was first established that Janus and Epius were separate objects. This encoding reminds me of a tree trunk encoding the number of years it has been alive by counting its rings. In addition to other stunning and detailed images of the rings, scientists have also noticed small propeller features scattered around them in various places. This image shows the illuminated and unlit sides of the rings, so they can compare and try to discern details. However, with the image's scale being only about 500 m per pixel, the moonlet may not even be resolvable. At best, it may be visible. In the top image, you can see a faint outline of the moonlet, but what's really interesting is that it's physically attached to the rings by this band of materials. As I mentioned before, there's another moonlet trying to create a gap in the rings. It's located next to the anchor gap. And here's the largest of the three. None of these moonlets are believed to be larger than 2 kilometers and likely have the density of a snowball. Finally, Cassini detected a tiny but solid object inside the rings. Objects that have developed near the earring, possibly as a result of disturbances from nearby shepherd moons. These objects appear solid because they have survived multiple impacts with the Fing, releasing dust and particles that sometimes follow their orbit. Nevertheless, the objects themselves are obscured by the dust, making them impossible to see. Lastly, let's examine Saturn itself. During Cassini's mission, Saturn's northern hemisphere was in full summer. As it zipped past, its unusual hexagonal shape became clearly visible. At its center was a permanent polar vortex, encircled by the eye wall of a massive hurricane. Interestingly, the color of the pole appears to be changing with the seasons. In 2012, it appeared quite dark. With the help of different light wavelengths, other storms could be seen all over the planet, and bands resembling Jupiter were visible, though not quite as prominent. Cassini's close approach to the planet allowed it to view the planet's horizon in stunning detail in natural light. On the left side of the image, a haze in the stratosphere of the atmosphere could be made out, but as the spacecraft entered the atmosphere on its final approach, scientists weren't too concerned that it wouldn't make it past this haze. What really piqued their interest, though, was the composition of the atmosphere that Cassini encountered. Would plunge into that atmosphere to retrieve that data, exploding in the process. These readings would be Cassini's last. However, just 1 week prior to its entry, Cassini continued to take images, and some of these final ones are truly remarkable. Now, keep in mind that Cassini cannot record video in real time, so the videos I'm about to show you are time-lapses created by combining numerous individual images into magnificent visualizations of what it would have been like to fly with Cassini on his. The first time-lapse we'll examine is from September 8th, 2017, which is just 1 week before Cassini's mission ended. The moon Enceladus was one of the prime candidates in our solar system for harboring life in its subsurface ocean. During Cassini's mission, the spacecraft found more than 100 water plumes erupting through the moon's crust. This water then freezes in space and forms. Cassini's last glimpse of Enceladus's plumes was captured in this breathtaking time-lapse that spanned 14 hours on September 11th. The E-ring surrounding Saturn is highly ephemeral, only becoming visible when illuminated by the sun. It is believed to be one of the solar system's most blue objects. Orbited Saturn and captured this stunning mosaic in natural light. The thickest rings, D, C, B, A, and F, are visible with Saturn's short shadow cast over them. Summer was in full swing in Saturn's northern hemisphere, revealing the planet's most famous hexagon storm in all its glory. In natural light, you can just make out Saturn's subtle bands. What's fascinating about this image, though, is that the night side of Saturn is dimly illuminated. As Cassini resumed his approach to Saturn on September 12th, he captured images of the planet's atmosphere near its terminator line. The sun is so low in the sky that huge cloud structures can be seen casting shadows that stretch for many kilometers. At first glance, you might think you're looking at a close-up of Saturn, but in reality, what you're seeing is actually. Observing the scene, one could easily fit Titan, Saturn's moon, which is about 5,500 kilometers across, into the shot. Cassini was drawing nearer to Saturn on September 13th, making its final appearance at Dives. Ripples were visible both in front of and behind the moon, caused by the different orbital speeds of the rings and the moon. The inner rings orbit faster than the moon, exposing more ring material to the moon's gravity, while the outer rings travel slower than the moon. On the same day Cassini took its final look around the solar system, it captured a view of Titan, a moon it focused on heavily during its mission, a remarkable world with a thick nitrogen atmosphere. It also appeared at Saturn's rings, with the uneven F ring just about visible at the bottom of the image. And as Saturn grew larger, it took its last look at Enceladus over a 40-minute period. This means that the ripples lag behind the moon by the time the ring material reaches Ness on either side again. The ripples have already smoothed out. Period before it vanished from view behind Saturn's limb, the last image Cassini ever captured was gazing over the area where it would plunge into the atmosphere. It was nighttime here, so Saturn was illuminated by light reflected off its rings. On the last day, scientists were in a rush to collect as much data as possible before the spacecraft was destroyed, so photos, as lovely as they are, took up too much bandwidth. This was a once-in-a-lifetime opportunity to probe Saturn. However, at its initial impact with Saturn's atmosphere, Cassini was traveling at a speed of 123,000 kilometers per hour. In order to maintain its antenna pointed at Earth, the spacecraft's thrusters were deployed. After 1 minute, the thrusters were fired at maximum capacity to prevent Cassini from spinning out of control. Cassini was now directly sampling Saturn's atmosphere, which was simultaneously heating it up. Just 10 seconds after this, the thrusters were fired again. Cassini's onboard computers would have been attempting to determine what was wrong when the spacecraft began to tumble and cut off communication with Earth. The gyroscopes and star trackers would have detected that the spacecraft was spinning, so the computers would have entered a safe mode to redirect power in an effort to write itself a message. A minute or two later, the spacecraft would have exploded in Saturn's atmosphere, and data would have started arriving on Earth 15 hours later. The last leg of the mission was widely recognized as a huge success. Cassini captured data from observations of Saturn's atmosphere, ionosphere, dust particles, and magnetic field, among other things. What's truly remarkable about the Cassini mission is that it continues to yield scientific papers and new discoveries as the data it collects is analyzed and music re-examined. What have we learned from Cassini's data since its launch? Saturn is the second largest, least dense, and sixth from a sun planet. However, despite its familiarity with its rings, the largest in the solar system, and its hazy yellow surface, both mysterious and easily identifiable, the planet remains a mystery, with a great mystery hidden beneath its obscuring atmosphere. This will be revealed in the upcoming groundbreaking Cassini mission. The Cassini spacecraft came to the gas giant on July 1st, 2004. Although it wasn't the first to do so, 3 others had already done flybys. The scientific community is still divided on how Saturn, whose behavior defies our standard models in every way, from its temperature to its magnetosphere to the length of its days. As previously stated, it spent 13 years circling the planet, gathering mountains of data using its spectrometers, magnetometers, and other instruments. While the knowledge it provided was invaluable, there are times when it simply adds to Saturn's mysteries. Consider the hexagon storm on Saturn's North Pole, which is 29,000 kilometers wide, and as far as we can tell, doesn't change its longitude, stays put, and moves with the planet's rotation. Of Saturn, unlike the rest of the planet's clouds, is being pushed along by winds of up to 1,800 kilometers per hour. This storm is definitely strange, and scientists still don't know what's causing it. However, there have been some lab experiments that have created small-scale hexagons that are close to the real thing, so it's not alone. When the mountains of data from Cassini's mission started to be analyzed, more mysteries began to emerge. It all began with a fairly innocent question. Saturn's thick cloud cover obscures any landmarks that might exist on any hard surface below, and those clouds move at different speeds to the core due to the powerful wind. The rings orbit Saturn at different speeds, so they don't settle. So scientists still don't have a definitive answer to the question of how long a day is on the planet. We've been watching Saturn in the sky for thousands of years, but it's not that simple. It is not possible to determine the rotation of a gas giant by observing its magnetic field. However, scientists have developed methods for determining the rotation of moons and rings by observing the speed of their orbits. These methods were intended to be applied to the Saturnian planets, which have magnetic fields due to the dynamo effect, in which the enormous motion of molecules in the planet's core causes massive currents of. Planets generate energy, which in turn create magnetic fields. One interesting thing about this is that, because of the planet's rotation, the magnetic pole is always at an angle to the planet's axis of rotation. If the two were to line up, the magnetic field wouldn't last long. So, all you have to do is detect the planet's magnetic fields, which Cassini could do, and then watch as the pole shifts in a circle around the planet's true axis. Once the pole has completed one rotation, you're good to go. Just make sure to include Saturn in this process. Saturn's magnetic field is 580 times stronger than Earth's and has a profound impact on the entire Saturn system. Scientists still don't understand how this field is generated, as it defies dynamo theory and no other known method of producing a field of this magnitude. On the other hand, the alignment of Saturn's magnetic poles with its axis of rotation is nearly perfect, with a discrepancy of less than 0.1 Da. It was back to square one for finding a solution. Scientists had to come up with a planetary dynamico in Saturn's core, but there must be another effect in the atmosphere distorting the magnetic field lines such that they are perfectly aligned with the axis of rotation. Luckily, radiation turned out to be more helpful. Saturn is an electrically live system, and charged ions move between the layers of its atmosphere, even between its rings and ionosphere. Observe that Saturn emitted radio waves due to its many magnetic fields. The intensity of these waves fluctuated, as one would expect from a planet that rotates, and scientists were able to conclude with some certainty that this corresponded to Saturn's day length. Their initial estimate, based on data from Voyager, was 10 hours, 39 minutes, and 23 seconds. They were hoping that Cassini could improve the accuracy of. This figure was initially attainable by Cassini, but things got strange when, over the course of his 13 years studying Saturn, it began to fluctuate by around 1% each year, sometimes increasing and other times decreasing. This seemingly indicated that Saturn was changing its own rotational speed, which would be completely out of the ordinary for a planet of Saturn's size, so scientists ruled out the possibility. Saturn's magnetic field is responsible for the planet's dazzling auroras, which light up the planet's poles. However, unlike Earth, where auroras are believed to be caused by the interaction of the solar wind with the atmosphere, Cassini found evidence that at least some part of Saturn's atmosphere is responsible for these stunning auroras. Saturn's auroras are not solar in origin, meaning that the planet is hotter than it should be and radiates over twice as much energy into space as it receives from the sun. While part of this could be explained by the planet's gravitational compression, the remaining portion required an explanation. Fortunately, Cassini's data provided us with one. Saturn is a gas giant composed mostly of hydrogen and helium. However, not all of this is gas. As one descends deeper into Saturn's atmosphere, they're subjected to intense heat and pressure. It is believed that this pressure converts gaseous hydrogen into liquid metal. Some scientists speculate that this liquid hydrogen, or even hydrogen compressed so densely that it becomes diamond, falls to the depths of Saturn's atmosphere. Some of Saturn's unusual heat is explained by the friction it generates, but the majority of it comes from the auroras. The exact source of these auroras is still a mystery, but scientists believe they are electrically charged particles that enter Saturn from its rings and moons. Whatever the case may be, the heat they generate is enough to warm the planet's upper atmosphere to dangerous levels, which in turn causes other effects like the formation of powerful winds where warm fronts meet cold ones, with theorized charged particles carried by the resulting winds. It is worth noting that there is a lack of conclusive evidence for many of these explanations, but it is possible that the ions in Saturn's upper atmosphere and the electrically charged winds are to blame for the distorted data from Saturn's radiation and its variability. Another possible explanation is that Saturn's magnetic fields are not where they should be, possibly due to a conductive layer within the clouds that is moving at a different speed than the others, creating its own fields. In order to solve these baffling mysteries, scientists are scouring the data collected by Cassini for any further clues. However, there is good news. The length of Saturn's day can be explained by looking at the rings. Instead of studying Saturn's electrical and magnetic effects on its rings, scientists discovered that Saturn would actually target them through its. This is all very obvious, but what really got under my skin was the realization that Saturn wouldn't target them uniformly. You see, Saturn isn't a perfectly round ball, and any variation in its shape causes variations in its gravitational field. The rings of Saturn provided the ideal canvas for observing these variations. When Saturn tugged at them with an increasing and decreasing force, scientists could detect ripples at certain locations in the rings and eventually located them by measuring the distance between them. Scientists were finally able to determine the length of Saturn's day, and they weren't far off: 10 hours, 33 minutes, and 38 seconds. Now that they're fairly sure they're correct, at least one mystery about Saturn is solved. The next mission to Saturn, led by NASA's Dragonfly, will launch in 2027 and explore Titan, the largest moon of Saturn. Titan is the most Earth-like object in the solar system, since it is the only place where Saturn's atmosphere is filled with nitrogen, similar to ours, but without oxygen. The planet has rain cycles and liquid legs on its surface, although they contain methane instead of water. Despite this, scientists are interested in studying Saturn, and it could be a while before the planet's deepest mysteries are solved. Saturn's winds, which could be its lifeblood, throb and flow through its atmosphere. The delicate balance of gravity and magnetic fields coax at it. The rings that encircle Saturn are believed to be relatively young, having formed within the past 100 million years. As they slowly sink back into Saturn's atmosphere, they could disappear in another 100 million years. This makes me sad, but I also feel strangely fortunate, because if humanity hadn't come at the right time, we might have missed out on this breathtaking cosmic sight. It might sound unscientific to say that. It's true that Earth doesn't have much say in whether or not it bestows gifts on Earth, but I'm still thankful for the opportunity to have witnessed Saturn's mysterious and beautiful world firsthand. The incredible Cassini spacecraft was responsible for collecting a wealth of scientific data that would not have been possible without it. After 15 years in Saturn's orbit, the Cassini spacecraft returned with data from a radio and plasma wave science instrument that could detect the sound produced by the gas giant and its moons. For our convenience, we compressed the radio waves, turning 30 minutes worth of data into 1 minute's worth of audio waves. This wasn't done for fun, though. The real scientific goal was to investigate where the radio waves were coming from. In this audio file, the source was Saturn's aurora borealis. You see, the sun is constantly releasing bits of its mass into space as electrically charged particles called solar wind. Planets with magnetic fields around them redirect this solar wind to their poles, where it impacts the atmosphere, specifically the ionosphere. Particles in the atmosphere become excited or collide, ionize, and then explode. Here you can hear the Cassini spacecraft as it navigates through the bow shock of Saturn's magnetosphere. As I mentioned before, Saturn has a large magnetic field surrounding it. The radio waves emitted by the aurora borealis can be seen by our own eyes as invisible light, but they also bounce around in the planet's magnetic field, where the Cassini spacecraft picked them up. In the first part of the audio, Cassini is outside of Saturn's magnetosphere, where the solar wind and the planet's magnetic field collide. At this point, the bow shock, Cassini's orbital path through the magnetosphere, is relatively calm and radio sources are quiet. However, after passing the bow shock, there's an abrupt spike in radio waves, and Cassini starts to pick up on a lot more radio waves bouncing around Saturn's. Here you can hear radio waves produced by lightning in one of Saturn's storms. They may sound tiny and almost puny, but keep in mind that this is not an audio representation, but rather the result of the planet's thick and dynamic atmosphere, which is noticeably different from the outside of the music magnetosphere. Cassini heard a lot more than just aurora. The spacecraft also made several close approaches to Saturn, listening closely to the planet itself. In order to get this close to Saturn, Cassini had to fly through its rings during flybys like this one. What do you think could be causing this audio? Cassini was traveling extremely fast around Saturn, reaching speeds of up to 121,000 kilometers per hour as it orbited through the Janus crater. Scientists estimate that the lightning in Saturn's storms is roughly 1,000 times stronger than typical lightning on Earth. Epimetheus ring, a faint and dusty ring, would make impact with tiny particles, which would then vaporize into clouds of plasma. Cassini's radio and plasma wave science instruments would pick up on these impacts, which would then be converted into the audio you're hearing now. The higher the frequency of these impacts, the densest part of the ring would be shown. As the impact subsided, Cassini would be seen moving away from the ring. Later in the mission, Cassini attempted this again, but this time using A. What happened the first time around? Well, it turns out that there were particle collisions, but none of the particles in that part of the gap were larger than what the RPWS instrument could detect. Cassini also carried another valuable tool, the Cosmic Dust Analyzer, which could detect particles as small as 1/1,000,000th of a millimeter. This tool did indeed detect an uptick in particle collisions during the FLYTH laughter through, and after the second FLYTH, you'll also notice these rising tones applause. The exact source of these is unknown, but they are similar to what Cassini detected earlier in the mission. On its mission, Cassini recorded radio and plasma waves from Enceladus, Saturn's moon, 2 weeks before it plunged into Saturn's atmosphere. These observations reveal a plasma circuit between Enceladus and Saturn, similar to that between Jupiter and Io, albeit to a lesser extent. Scientists were surprised by the strength of this plasma circuit. Cassini's magnetometer allowed it to detect this. During its flyby of Enceladus, the probe detected a bending of the planet's magnetic field, which is indicative of a thin atmosphere. This thin atmosphere is likely caused by jets and cryovolcanism near the tiny moon's south pole. The geological activity here is similar to that of Jupiter's moon Io, where the two planets' magnetic fields interact strongly with the moon's ejected atmospheres, forming a flux tube or current of charged plasma particles. There's one more location I'd like to check out on my own. Titan Cassini's primary goal upon entering the Saturn system was to send the high-end probe hurtling towards Saturn's largest and most intriguing moon, Titan. While the probe lacked an RPSW, it did have other instruments that you can hear as it dipped below the surface of Titan. Radar echoes, which the Hyans used to measure their height above the surface. And this, my friend, is the most astounding thing about it all. In comparison to the other clips I've shared, this one doesn't sound very impressive. However, when you consider that the audio was recorded by a microphone on the Hyan probe as it dipped into Titan's atmosphere, you can hear the exact same thing that someone sitting on Hyan would have heard as it dipped. This adds an incredible sense of wonder and perspective to the clip, one that I've never experienced before. There may be other planets out there, but I'm not sure if there's anything quite like this. And now we have the sounds of Saturn and a couple of its moons. I'm really excited to show you Saturn today because it's one of the most amazing planets in our solar system. I think you'll agree with me by the end of the video because the Cassini probe has given us some incredible images of this stunning planet. My name is Alex Mullen, and Saturn is the second largest planet in our solar system, with an average radius 9 times that of Earth. Its equatorial and polar radii differ by almost 10%, measuring 60,000 kilometers at the equator and 54,000 kilometers at the poles, respectively. In this video, I will share some breathtaking Cassini images with you and provide a general overview of nearly everything you could ever want to know about this gas giant. Saturn is the lightest planet in our solar system, with a density that is around 7 g per centimeter cubed. Its massive volume makes it nearly twice as dense as Earth, but its low density makes it the heaviest planet overall. No other planet in our solar system is denser than water, which is around 30% less dense. In fact, if you had a bath toy of Saturn that had the same density as the planet, it would float because it is composed of 96% hydrogen, the lightest element. Saturn is classified as a gas giant because, from what we can see, the planet is entirely gas and lacks any rocky surface beneath its cloud cover. However, the planet's mass prevents it from being completely gaseous. As one travels deeper into Saturn, the pressure builds, and eventually the hydrogen ceases to behave like a gas and starts to behave like a liquid. In a way, underneath Saturn's atmosphere, which is a liquid ocean of hydrogen, there may be a metallic hydrogen layer where the pressure is so high that hydrogen starts to behave like a metal. Beneath that layer, there may be a metallic and rocky core. Saturn's interior is known to be extremely hot, reaching 11,700 C at the core, which is twice as hot as the surface of the Sun. When we observe Saturn through infrared, we can see its glow reflected in dazzling shades of electric blue, sapphire, and mint green during the night. Side of Saturn where sunlight doesn't reach, the planet's internal thermal radiation illuminates the surface. This radiation originates from deep within Saturn and travels upwards, eventually escaping into space. As you can see in this infrared image, Saturn radiates 25 times as much energy into space as it receives from the Sun. You might not have noticed, but Saturn's atmosphere has a banded pattern, similar to Jupiter's. If you increase the contrast when looking at images of Saturn, you can magnify Saturn's bands. Saturn's winds are the second fastest in the solar system, behind Neptune. It can reach blistering speeds of 1,800 kilometers per hour. Visible storms, such as the one that lasted just under a year in, do occur on Saturn, though they are less chaotic and wider near the equator. If you've ever wondered why Saturn is yellow, it's thought to be because of ammonia crystals in its upper atmosphere. According to the Cassini mission's conclusion a few years ago, we will only be able to observe Saturn's smaller storms through the Hubble Space Telescope. However, there has been a 30-year pattern in which the planet has produced what is known as a great white spot, a unique but fleeting phenomenon that is believed to occur once every Saturnian year. We have seen multiple of these spots in the past 30 years, so we can expect another one at any moment. While we're on the subject of storms, it's worth noting that Saturn has enormous, permanently occurring storms at both of its poles. In November 2006, NASA announced that Cassini had detected a hurricane-like storm lock to Saturn's southern hemisphere, a persistent hexagon-shaped storm that rotates with the planet, not with the atmosphere, has never been seen on any planet before except Earth. Its eyewall clouds resemble a hurricane's eyewall, but are much larger. The center of the ring is warm and clear, like the eye of a hurricane, but Saturn's ring is locked to the pole, unlike Earth's hurricanes, which drift around the North Pole. The straight sides of the polar hexagon are about 13,800 kilometers long, making them bigger than Earth's diameter. Why does this happen on such a massive scale? Well, we don't really know. However, Recent lab tests have shown that unusual polygons can form in a circular tank of liquid when the speed differential and viscosity parameters between atmospheric bands are within certain margins. This theory is currently leading the pack, so it's worth keeping an eye on. At the very center of this hexagon lies another eye wall, although it is far weaker than Jupiter's. Saturn, like other planets with magnetospheres, has auroras, the location and intensity of which are highly dependent on the pressure of the solar wind. Auroras grow brighter as they approach the Sun, and the planet's magnetosphere extends far beyond Saturn itself. Polar regions experience an increase in solar wind pressure, which causes auroras on both Earth and Saturn. This process involves electrons from the solar wind flowing along lines of magnetic fields into the upper atmosphere, where they collide with atoms and molecules, expending this energy in the form of light at various colors and wavelengths. On Earth, this light primarily emanates from oxygen and nitrogen molecules, while on Saturn, it is primarily from hydrogen. Personally, I find the rings to be one of the most fascinating phenomena in this process. The 10 main rings that make up Saturn's ring system are mostly named after letters of the alphabet, which can be a bit confusing at times, but bear with me. The first 5 rings, starting from the one closest to the planet and working our way outward, are the following: the faint D ring, the C ring, the B ring, which is the brightest and widest of the rings, the A ring, which is the last of the large bright rings, and finally, the F ring. The rings extend from 66,000 kilometers to 140,000 kilometers above Saturn's center, and they are. The composition of the rings is primarily water ice with trace quantities of dust and rocks. When examining a UV section of the brightest rings, it becomes apparent that the outermost rings contain more ice than the innermost ones. The color red in the image suggests that the red ringlets are likely comprised of smaller, less pure particles compared to the turquoise ringlets. By comparing these red ringlets to a radioelation picture, we can estimate the sizes of the individual particles that compose the rings. We can observe that the rings are not perfectly symmetrical during the planet's equinox. Shades of red indicate regions where particles have a diameter greater than 5 centimeters. Green indicate regions where particles have a diameter smaller than 5 centimeters, and blue indicate regions where particles have a diameter smaller than 1 centimeter. On the whole, we can conclude that the particles in the rings are microscopic in size, with a maximum size of 10 m. The main rings, meanwhile, are believed to be anywhere from 10 m to 1 kilometer thick. At the beginning of this video, you can see the B ring meeting the A ring. Zooming in on the structure reveals ridges and spokes that are a couple of kilometers tall. Their presence is indicated by their shadows. Zooming out again, we can see the scale of how many spokes there are during this period. Oscillations occur frequently in the rings, either because of shepherd moon or simply because of natural variations. In a single day, differences of up to 200 kilometers can be seen. So I've covered the D, C, B, and A. In addition to the FR ring, which can become quite wonky at times, there's an excellent example of a shepherd moon in Prometheus, which causes a lovely ripple in the E-ing as it orbits Saturn once every 147 hours. At the point in its elliptical path where it is furthest from Saturn and nearest to the Thing, Prometheus's gravity is just strong enough to pull a streamer of material out of the core region. This picture is absolutely mind-blowing. The E-ing's bright blue ring, the Janus or Epimetheus ring, the G ring, Payne ring, and finally the E ring are all clearly visible under the sun's rays. Up top, you can barely make out the Payne ring, but that's all. Then, there's the G ring, which is the next distinct ring, and you can barely make out the Janus or Epimetheus ring, which is just barely visible. It's likely that the recently discovered Phoebe ring, a massive yet dispersed ring that extends far beyond Saturn, came from Saturn's 200 kilometers wide moon Phoebe, which has been battered in its past orbits and likely keeps this dust contained from interplanetary collisions. At the top of the picture, below it, and can you see us? We're all in this picture too. Here is Earth and the Moon. Now that you know about the rings, I think you all agree that they are fascinating in their own right. On the other hand, there's a theory that suggests dust from this ring is falling inward and eventually into Iapetus, Saturn's outermost regular moon. Iapetus takes on a bizarre combination of colors when dust from the Phi ring settles on it. However, because Iapetus is neatly locked, only one side of the moon ever faces Saturn, while the other side is exposed to the Phoebe ring, so its two faces look very different. Saturn has at least 802 moons, and they come in all shapes and sizes. Titan, Saturn's largest moon and larger than Mercury, is the only moon in our solar system with a thick atmosphere. Theories abound regarding their purpose, but we still don't know for sure. We do know that some of the moons are responsible for some of the material there, and we also know that some of the material there is responsible for some of the moons. While most of Saturn's moons are just a few kilometers across, the titular Death Star is in orbit around the gas giant. Now let's talk about Saturn's orbit. It's 9 to 10 times farther from the Sun than Earth's orbit, and a year on Saturn takes 30 Earth years. Interestingly, the length of a day on Saturn varies depending on whether you're at the equator or the poles, but it's roughly 10 hours long. 14 minutes on Saturn and 10 hours and 38 minutes everywhere else in the solar system. The problem is that Saturn isn't solid, so its rotation speed isn't uniform across the entire planet. I like to leave you with this thought. There are few solar system sites as stunning as Saturn, a gas planet embraced by its rings and displaying a subtle northward gradient from gold to Orius. Scientists still don't completely understand this effect, but current theories suggest it may be linked to seasonal changes, influences connected to the cold winter hemisphere temperatures, and, despite everything we know about Saturn from Cassini, the planet itself is still a mystery. Thank you for watching this video, which was made possible in part by the astronauts on Patreon. If you believe these videos are educational and would like to give them more longevity than the algorithm allows, you can become a paid member on Patreon and contribute to their creation. When you join, you'll have access to all of our videos ad-free and see your name in the credits. Thank you so much from the entire Astrum crew. To get credits and ask questions, simply sign up using the link in the description. In the meantime, you can click on this playlist for more Astrum stuff. Until next time,